So this is the how you can run MPI program. So and these things in last class also I've discussed. So sum of n data. So in this case, so master process it data to be read from the process 0 means you can read data from the means, keyboard or any files or any places, and divide the data into n by m chunks and send the respective chunk of data to the other process. Do the local sum on the process in master also means because suppose one is master and another 4 is worker. So then you divide the data into 5 chunks, and one chunk master will do, 4 chunk other worker will do. So and then receive sum from other process and calculate the final sum. Okay, and the worker what will do? It will receive the data from master, do the local sum calculations, send the local sum to master. So in this way, means multiple processes can collaboratively do a bigger work. And whenever saying bigger work, that means this summation of n data, this n need to be much bigger. So then only you will get effectively means with less time. And if you want, already I have seen the demo of this code, so we are not going one more time. So then this code, let's see for matrix multiplication, what will be the how we can parallelize the matrix multiplication. Very crude way of doing the parallelizations. So C is equal to what we are trying to do. C is equal to A cross B we are doing, and what is the number of row means number of column NRA and NCA. This is number of row and number of column in A, B, and C. These are the number of row in A, number of column in A, number of column in this is NCA, NCB, and NRA and NCB. So this is a 3 array we are taking. Okay. Then how we are dividing? So we are dividing by means number of row of C. Okay. Ultimately, number of row of dividing C is similar to actually means whether you what Cij is equal to what we do. So ith row we take up A, and then whole B we do. Okay, all columns. Ith row it's need to iterate for all columns. That means whole B we require. See, for calculation of Cij, we require ith row of A and whole B, all column of B. So what? How we divide? We divide the work. So you can see. So this red part, processor 0 means suppose there are 4 process, and process 0 calculate on red part. Okay, of C, and which require red part of A and whole B. Similarly, processor 1, 0 and 1. So processor 1 need to calculate. Suppose you want to calculate on the area of this blue area, then he require data blue area of A and whole B again. So ultimately we are dividing by row wise. So on master, so there are many worker. Assume means number of worker is equal to NRA number of worker is equal to 0. Then what do you do? So master divide the work between workers, send respective row of A and whole B to the worker. So if you look at the code, so for calculation of blue area in C, the worker require blue area of A and whole B. So what you are trying to do? So send respective row of A and whole B to the worker and receive array C from all worker. So whenever I'm saying receive array C from all worker means, so there will be for loop for 0 to number of worker, and it receive one after another, part of C, part of C, part of C, and part of C. And what every worker will do, get some row of A, then whole B. So whatever I have signed here, so that thing we are getting from here, and calculate part of C, and then let's send the calculated C to the master. So in this way, means we write MPI program. So how we divide the work, okay, among different processes or different worker. So let's see the code. So this code is what we are doing. We are using basic send and receive procedure. Okay. Very basic send and receive procedure.
Sir, can we use gather and scatter in this case?
So, no. So that will say, we'll give another example. So how it can design. So this is one way of designing. If you want, we can design using scatter and gather also. But this is one way. This code is for send and receive. Using send and receive, we have designed the code. Okay. And how we are doing the things. So based on how we organize your program. Okay. How we have divided the work and how they are coordinating. Based on that, what kind of what I can say collective communications we want, or you want individual communications. In this case, we are using individual communications. Master is sending data to what I can say worker, and after the worker is sending back the data to the master, and master is receiving. This is a very simplistic way. So in this
Sir,
case, yeah.
why don't we divide B based on columns and send it?
So we require a whole of B in this case. We are dividing in this way. So if you look at this thing, so to calculate the this blue part of C, we require blue part of A and whole B we require. So in this way, we are dividing. So you can write a different program. How you are dividing the work among the process, you can decide. So in this way, so in this example, so we are doing in this way. This matrix manipulation can be done in many different ways. Are you getting my point?
Yes, sir, got it.
So in this case, we are doing in this way. Okay. So what master is doing, so initially if you look at the code, so starting int main, whatever you are doing, and here declarations, double A, B, C, so NRA, NCA, NCA, NCB, and NRA and NCB. So these are the declarations, and these double variables are actually, if you look at these variables, are local to a process. So suppose you are creating 5 process, then that means for all 5 process, this variable will be local to them. This is not shared variable. This is local variables. Even this number of taxes, number of worker, destinations, rows, offset, all the variable will be local to the process. Okay. So every process will have all local copies. And whenever you are executing MPI init, then MPI comprehend, MPI comp size, these are actually all what I can say MPI routine. Whenever MPI routine is not local, it runs under the MPI environments. Okay. So this is MPI init we are doing, then MPI comp rank. It's how many, what is the rank of own process? Okay. Then it is what is the total number of process we are getting, and then this is the master. What it is doing? Master is trying to initialize array A and array B. So that means it is initializing. It may take data from file, or it may take data from any other sources, or it may take data from keyboard. Okay. So master is getting the data in this case. Master is getting the data from A or A and B. And after that, so in this case, what is the average number of rows? And this is the extra number of rows. So if it is divisible, then extra will be 0. And this is the offset. So for master, offset is 0. Okay. For other, offset is rows, number of rows. Okay. So what we are trying to do, rows is equal to, this one is extra plus average rows. And here, master is, hello? I think so. We need to mute all to all. Otherwise, so in this case, master, what it is sending. So are you able to see the code? So it is sending offset. Okay. So what is the starting point? So for master, offset is 0, but for other, offset is increasing. Okay. So offset is increasing. So what is offset? Then what is how many number of rows it is sending? Okay, and after that, this is the actual data of A. So rows into number of column in A. So number of rows, average number of rows, or number of rows required by the worker, number of rows required by the worker, and this is the number of column of A. So this is part of A it is sending. It is sending part of A. And in this case, it is sending the whole B. It is sending the whole B. So if you look at, so array B is available in master only. Other places, the value will be garbage. Other places, they have the array, but the value will be garbage. They will not have the actual values. Okay. But here master is creating the values. Master is getting the value of A and B. Master need to send the value of part of A and whole B it is sending. And after sending these things, so what is doing? So if you look at, after sending this, master also doing the computations. Here, this is after this computations, what is it is doing? So if you look at, it is receiving the data. So, and every process, if task ID is greater than master, so then what they are doing? So receiving offset, rows of A, part of A, require part of A. Okay. This is offset, and this is a number of rows, and require part of A's. This is require part of A's, and this is whole B. We're getting whole B. Offset, number of rows, require part of A, and this is whole B we're getting. And after that, here it is locally calculating. Every worker is calculating the part of C. Okay, every worker is calculating part of C. After calculations, it is sending offset. What is the number of rows? What is the number of rows it is calculated? And that whatever the calculated part of C, the calculated part of C, and this will send every worker, it will send after the calculations, offset, rows, and calculated part of C, and master will receive that part. If you look at here, master is receiving that thing. What are the things receiving from worker? It is receiving offset, it is receiving rows, and part of calculated part of C. It is getting the calculated part of C. And after receiving, so in this case, if you look at, for I is equal to 1 to number of worker, it is getting from everyone, one after another. So similarly, sending also it is doing one after another. So here also sending one after another. For destination is equal to 1 to number of worker, it is sent. Then everyone will calculate it there after receiving. Then they will send to master, and master will receive one after another. And once master receive all the work, okay, so all the data, then it will display the result. It will display the output. So is this clear? So we can compile this code. So what is something? Oh, MPSCC.
MPSCC.
So MPSCC. Okay, so a.out we got. Then MPA run. So MPA run minus NP. So suppose you want to run on how many processes? It depends. So suppose you want to run on 10. 10, then a.out. So it will run on 10. It will run on 10 processes. So if you go up, then it is saying, so initializing the array, MPM has started with 10 taxes, initializing the array, sending 7 rows and this thing. Okay. For 9 worker it created, and it sent 7 to 8 process and 6 to last process. And then After that, it is receiving the work and printing the work, printing the result. So in this way, we can write MPA program. Okay, and what we are doing is here, we are running these things on local machines, only one machines, and you can do 4 process, any number of process we can do. So it is running on 4 process. It created 3 worker. Okay. So this is a MPA example. So one MPA example we have some. And suppose you want to run on actually permissions, then what you need to do? So you need to create, you need to run instead of MPA environment. Okay, instead of this MPA environments. So what we are doing, MPA run minus NP4 a. This is for local environment we are running in this way. Okay, for running in what I can say permissions, the environment will be different, but the coding style will be same. Okay, coding style will be same, but running environment will be different. So that will be run by SLURM. So that is called Slum script. So we need to submit the job, and job will be running there. Okay, so this MPI job a.out and how many number of process. Only these informations will be submitted as a script in a script. That means this is a job a.out with minus NP4. This will be as a job, it will be submitted to the system, and the slum scheduler will run on multiple machines. And this NP minus 4, in this case 4 process per saying, but you can write maybe 1000 process or 2000 process also. Okay, based on requirement. Okay, so let's go for another example. So this is already we have seen in this case. So what we are trying to do is in this case, we are trying to calculate value of pi by doing a trapezoidal rule. So pi is equal to 0 to 1, 4 by 4x, 1 plus 4x square dx. So this is function is 4 by 1 plus x square. And this function should be integrated from 0 to 1, we will get value of pi. And we want to calculate the value of pi by using trapezoidal rule. Okay. So what trapezoidal rule means divide the range, the whole thing. So we want to calculate area under this curve. Okay, from 0 to 1. Okay. And what we want to do? So divide the range into n interval or pieces. So piece size suppose h, which is range by n. Calculate the area under each piece. Calculate the functions value at each piece and multiply with the piece size. So h into fx will get the area under the piece. Okay, area under each piece. So it is this is piece. This is one piece. This is one piece. And sum all the pieces, then you will get actually value of pi. So this is the standard integrations. So by numerical methods, we know these things. Okay. And how we can do? So write an MPA program. This is suppose C program. Suppose you write C program. So printf enter the number of interval. So n is number of interval we are taking from keyboard. Then calculating h. So 1 by n. So 0 to 1. So range is 0 to 1. That is 1. And initially summation is equal to 0. And for I is equal to 1 to n. So x is equal to h into I minus 0.5. Then what we are doing? We are calculating functions fx at point ith piece. At ith piece, what will be the values? Okay. So fx is equal to 4.0 by 1 plus x square, 1 plus x square, whatever the functions. Function was this one, 4 by 1 plus x square. Same functions we are calculating, nothing else. Okay. And what is the value? X is increasing from 0 to 1 with steps. Okay. With h. Every time we are incrementing h. Or what you can do, we can take average point, h into I minus 0.5, middle point, that also fine. And after calculation of that thing, so what we are trying to do, sum is equal to sum plus fx. Whatever got the values, we are summations, doing summations. And part of the final summations, h into sum. Finally, h into summation will be the value of pi. This is a simple C code. And how we can parallelize this thing? Suppose n is number of point is not 1 or 2, but is million points. If you want to calculate for million points, then how you can do? So kind of 1000 points. Suppose n is equal to 1000 and number of processor or process is 4. So in parallel, you can calculate like P0 will calculate x1 point, then x5 point, then x9 point. So P2 will calculate x2, x3, color coding. So red color will be calculated by red process, then blue color, then magenta color, then black color. So color coded is given. So in this way you can calculate. So ultimately, after getting this thing, these summations. So red have calculated the sum points, blue have calculated some points, magenta have calculated some point, black have calculated some points. Then after that, we get the summations. So in this way, we can. This is one way of writing the parallel program for computation of pi. Okay, for this kind of thing, we can. This is the work division. How we are doing? We are deciding. Based on that, we are writing program. And this is the simple program. So initially MPI init we are doing, then com size and rank. This is very common code for all. So how many process n process we are doing, and then my ID. This is rank. This is total size. And if my ID is equal to 0, that means this master process is getting value of n, and after that it is broadcasting n to all the people. Suppose number of process is equal to 10 or 11, then 0 process is getting the value of n from keyboard, and then it is broadcasting the value of n to all the rest of the 10 process. Clearly, what I told you earlier, the MPI broadcast, this MPI, all the MPI functions, it is not local, it is global, and this is collective operations. This is collective operations, collective communications. This is not one-to-one communication. What we are doing, it is collective communications. And after that, each process will do, this is collective communications, means control will come to this point, do the collective operations. Okay. Then again, after doing the collective operations, again it will start the executions. Okay. So here edge is equal to for their part. Okay. For their area they are doing. That means every time I is equal to I plus n process we are doing. Not I is equal to 1 to n we are doing. In this case, I is equal to I plus n process. That means whatever in this case 4 means every 0th guy, then 4th guy, or 1th guy or 5th guy who are doing. A number of process is 4. So in this case, I is equal to I n plus process, and then we are calculating x. Then we are calculating, this is the functions, and we are summing up. And after that, we are calculating local sum. Every process will do calculate the local sum. They are calculating the local sum. How many local sum will be calculated? Suppose number of processes is 4, means 4 local sum will be calculated. And once everything got calculated locally, then what they are doing? MPI reduce L sum ampersand pi 1. What is the 1 is destination place. MPI double, and what operations? MPI sum operations we are doing. So this is collective communications. All process do these communications collectively. Okay, so what if you look at the flow of executions? So everyone will execute up to this point. Every process will execute up to this point, and they will wait for the broadcast. Okay, so this is barrier. Once everyone get synchronized, then only this broadcast will be executed. Then after broadcast everything broadcast is done, then everyone will execute up to this point, and they will stop, and they will wait for the reduction operations. Okay, then everyone will execute the reduction operations, and because we are reducing at 1, finally sum will be where it will be reflected. So sum will be reflected at, I think so, this is sum, this is 0th places it will be reflected. This is 1 data, and this is 0th process it will be reflected. And after doing this reduce collective operations, then my ID process 0 means 0th process will print the value of pi, and then MPI final edge. this finishes the MPI program. Is this clear? So here, this program we have written using collective operations, not using send and receive. Is this clear? Hello? Hello?
We are putting 0 because we want to broadcast n from the master to everyone else in the same
Yeah.
manner.
Yeah. So in this
Sir,
case, if you look at this is broadcast from 0, and this one is reduced to 0, reduced to process 0. So all values from LSUM, means local process LSUM, will come and collectively come into the value of pi. Okay, so value of pi at process 0. Is this clear?
excuse me, sir.
Yeah.
Yeah, sir, if there are global variables in a program, then are they still considered local to the process?
Local, because it is different process.
Okay.
Even if it is global variable, so they are local to that process. If it is multi-threaded or OpenMP1, that is said, but because these are different processes, even if it is global variable, it will not be means kind of shared by different process. It will be local to that process. Is this clear?
Yes, sir.
Okay. So these are the two examples, matrix multiplications. Last class we have given summation of n number. The three examples we have given how to write MPI program, and you can run MPI program. Okay. Whether I have let me see. MPI pi is there or not? I don't know. This is using send and receive. You can do the same thing using send receive, not collective communications. Serial pi calculation. This is the serial pi calculation. There is. I think so. I have not written code. So otherwise I could have given demo. Okay, that's fine. So if you look at IITG means cluster permission, we have 4 login node. So 126 compute node, 16 GPU node, and 16 5 compute node, and total 156 node, and plus each node have 12 core, 2 threaded, and effectively how many cores? So 24 into 158, so 3792, so 3800 around cores. And login node means for non-GPU and P. So this is the login node. So whenever you compile MPI code, so just log into the login node, then compile the MPI code in the login node, then run using srun or sbatch. Okay, so their environment will be different. So in sbatch, specify the number of node, tasks per node, and total number of process to run the MPI code. So some student wrote, can you show demo how to run MPI program on multiple nodes? So this way we can have actually, if you have a login in MPI permission, then you can write MPI program and permissions. So I don't have personally, I don't have any setup to show run MPI program on multiple node. But definitely we can run program on permissions. So Slum is simple Linux utility for resource management. So scheduler schedule the job efficiently user don't need to worry about where it is getting scheduled. So user only, they specify the number of process, okay, and how many number of processor they want. Number of process, how many node, how many tasks per node they specify. They don't say which node and how it will execute, and that thing the user will not bother about. Okay, so do you know when in our IIT Guwahati, which department people are the most efficient or most what I can say usage we get from the permission usage we get from not from CS department or E department. We get most of the permission usage from chemistry, chemical, then bioscience and mechanical. We get most of the usage from mechanical, bioscience, chemistry, and chemical. So they run very highly compute intensive job, simulation job on permissions. This is for your yeah.
So I had a small doubt in the last slide.
Yeah.
Could you go there? So in the last, yeah. So here you have written no in the next. So here you have written total 158 nodes, right? And in each node there are 12 core, all right? And for each core you have specified 2 threads, right? So how can we specify the number of threads for a core? I mean,
so we don't specify this. If you look at Intel processor or i5 processor, okay, i5 or i3 processor. So i5 processor internally they have 2-threaded, so 2 hyper-threaded. So whenever you run OS on top of your machines, then it will show so 8 processor. It will not show actually 4 processor. Even if it have 4 processor, okay, each processor have 2-threaded. The OS will show there are 8 processor.
okay.
8 simultaneous.
So
So
suppose I have a machine with only one processor and one core, right?
Mhm.
This machine can allow multi-threading, right? Using SMT.
Yeah.
So I don't get this notion of specifying the number of threads for each core. I've read this at other places also. This is very confusing.
No, not confusing. So this 12 core into 2-threaded, whenever you say 2-threaded, this is hyper-threaded. Hyper-threaded means it's hardwarely it is threaded.
Okay, so what is this, sir? Hyper-threading?
Hyper-threaded means suppose you take let me show you means any my screen is here. Okay, so Arc, Intel, so some processor I'm doing. Okay, so are you able to see my screen?
Yes, sir.
So it is getting data from this thing. Okay, so if you go, that is what it is saying. It is getting okay. It's fine. So number of core. So in this case, we're getting in some different language. So that's why look a little bit odd. This is Brazilian language. It is getting.
Portuguese.
Yeah, something. Okay, so let's change to English language. Yeah, so I got English language one. Otherwise, you will not be able to understand. So now it is fine.
Yes, sir.
So this is Intel i3, so 10110. So this is total number of core is 4 and total number of thread is 8. So if you have system with Intel this processor i3 10100, then whenever you run OS on top of this, it will actually show 10 cores, 8 cores instead of 4 actual cores, because this 4 into 2 is equal to 8. Each core have 2 hyper-threaded means what I can say hardware threads.
Okay,
It
so
can
this is
run
not
2 hardware threads on the core.
So
That
this
means
is hardware.
OS will see there are 8 cores.
Okay. So this is
OS
all
will
the chip,
there are 8
right?
cores.
This is
This
this
hyper-threaded.
is the chip, actual physical separate units of computation, right?
Yeah. So
Over.
it will do internally. Processor will do internally.
Okay.
OS will not get to know that whether it is staying internally or externally.
Okay, so OS is 8 cores here, right?
OS will see 8 core.
And over the top of those 8 cores, I can always run a multi-threaded program, suppose 16 threads.
Yeah. So
Okay, then that is fine, sir.
so
Okay.
that's why OS will see 8 core in this case. So that's why in this slide also what I mentioned is, so there are each node there are 12 core and this is 2-threaded. That means it will OS will see 24 core per node.
Okay, sir. Thank you.
Got it? Okay. So in your OS also, let me see whether my thing is i5, but i5 I have actually system monitor. So you can see your own thing. Are you able to see? This is my i5. i5 have 4 core and each core is single threaded, not multi-threaded. That's why I'm able to see only 4 core. So in your machine you can check. Okay, system monitor. Go and see system monitor. How many core you are getting? So in what I can say, window environment also you can see Mac environment also you can see. All environment you can see resource manager and you can see how many cores the OS is showing. You got my point? It's fine.
Yes, sir. Yes, sir. Thank you.
Okay. So this MPI program. So if you want more MPI program, there is a tutorial. Okay. So LNLL tutorial, and there is a very good book by Bipin Kumar and Anant Grama. So this is Introduction to Parallel Computing, and they are actually producer of actually graph partitioning arguments. What is the software they wrote graph partitioning software is called Metis, and there are another very good book by Parallel Programming in C with MPI and OpenMP by MJ Quinn. And if you want to know many high-level things about parallel algorithm, so this book don't deal with actually what can MPI program. So it will deal with everything with parallel algorithm, how you can parallelize a code. And there is a very good introduction to parallel algorithm by Joseph Jaja. So this is very, very old book, standard classic book, already 30-year-old book, but still many people refer, even I refer this book always. Okay. And next week, what is the time? So we have time, I think so. Still we have 10-15 minutes. So now whenever you write MPI program, so MPI program run on multiple node. And MPI program don't assume so where the node is, how the OS is scheduling. But sometimes what happens, so MPI give you flexibility of writing program using multiple processes. It don't say where this process will go and executes. But in general, whenever you want to get more performance, then sometimes we need to go and see what is the internal also. So how these processors are interconnected, how this OS is scheduling, where the data is stored. Okay, so that thing we require. So basically, how they're interconnected, at least we should know. Okay, so if you know how it is interconnected, you can write a better MPI program. Because I want this process 0 will allocate to core 0 and core 0 will have actually central node and it will actually have connected in star person, then it will be better. So if you look at simple MPI program, send and receive. Suppose the master node is connected to all the worker node in star persons, then each way of doing will be much better because we have written the code in a star persons manner. Okay, so master is sending data to all the worker and he's getting data from all the worker to the master. That means if all the node is connected to the worker in a star network, then definitely means you will get a better result if you write that kind of code. Suppose your network underlying network is star network and you write that kind of code, then it will match properly and you will get better performance. Suppose your underlying architecture is completely different, then your performance will not get as much as you expect. Okay, underlying architecture have also some effect on performance, but MPI will give you flexibility without specifying the architectures. We can write parallel program. You got my point? So whenever you write C code, so do you look at what is the processor architecture? Students, in general, no.
No, sir.
There is high level, there is the logical level. So logical level is very good for understanding. Okay. So whenever you write some data to, suppose you are creating a Word file, do you see that your Word file is getting written into your hard drive or SSD, or you are writing to a network file locations or any places, or you're writing to a Google some cloud place, you don't care. You write on the high logical level. So similarly, so MP provide you the view of logical level, but sometimes we need to run the code on actual platform. So actual platform a different network. Okay, so computer interconnection network plays the most important role in this thing, and generally how this means network get interconnected. So number of nodes get interconnected. So very simple methodology is actually you connect all the what I can say machine or processor with simple bus arbiter, and you can use shared memory kind of architecture, bus arbiter. But this bus arbitrations connecting using a bus, simple bus. So there is a limitation. Bus connections is very easy. What is bus connections? Everyone is hooking to the common bus. So that is actually very easier way to connect, but it has also some demerits. So bus connection, very funny example is suppose you create a 2+2 highway, then everyone will jump into highway and make their own house near to the highway. So that actually get congested. Okay, even if you are making if everyone do that thing, that will be congested. So that should be some policy. Similarly, so in computer system also it has similar things. Bus interconnection is very easy. Okay, but it is after 8 or 10 nodes, the bus get congested because it is shared medium. Suppose P1 want to send this processor want to send to this processor, then whenever it is sending this data, other processor will not be able to send to other places because it is common share medium. Common share medium is easy, but it has some difficulty. Everyone need to go through queue. There must be some arbiter or control to control the communications. At a time, only one communication can happen. So which is definitely it is a demerit. So this is bus protocol, queuing based bus protocol need to be there, and there must be some bus arbiter or grant based on policy or priority on sending and receiving the queue. Okay, source and destinations. And most common policy we were not specifying anything, then FCFS policy people use. And general bad it is utilization saturate with number of requests and saturate more quickly as processor increases. So if you connect 8 to 10 processor in shared medium, then you will not get much performance. So bus interconnection is very bad if number of machines or number of processor is more than 8. So large collection of computer, so connected using network. So example of grid system, geographically at different locations. Data centers, so many container or static network, many racks in a container, then many chassis or rack in a server, many server or socket processor or chassis or quick path interconnect or bus inside a server, then many cores inside a socket or processor, and many hardware thread in a core. So whatever I told. In data center, what happens? So many hardware thread in one core. So Intel and AMD, they are putting 2 hardware thread per core. Okay. And many core in a processor, many processor in a rack server, many rack server in a rack, and many rack in a container, and many container in a data center. So ultimately, what do you see like this permission? So this is the whole permission. So our institute permissions. Is this are you able to see the photo? Hello?
Yes, sir.
This is the permission. From outside, it look like this. So this is the whole data center. Okay, data center means whole HPC system, and it have many. What I can say? It have many container. Data center have many container. Are you able to see container? This is one container. This is another container. Many container. Okay, many container. Container have racks. Rack have chassis rack server, and one rack server means. Have you heard about rack server? You have heard about PC. You have heard about what I can say laptop. But rack server means. So in
They are blade server that are designed specifically for computing purposes.
computing purpose, and we generally put into the rack. We generally put the things into rack. So these have actually rack. So this is rack. So this is whole thing is one container, and this is one rack. and inside this rack, we have many rack servers. So let me show you other diagrams so that will be more clear. So are you able to see the rack server?
Yes, sir.
Yeah, so this is the rack servers. Okay. So rack servers, and each rack server have actually many processor. Each processor have many cores, and each core have many hardware threads. So in generally Intel Xeon processor now each processor have actually around I think so 40 cores and 80 threads, or I think so 32 core and 64 threads are there Intel Xeon processor, and AMD also they have around 64 core and 128 thread. Okay, so if you look at the high-end server, so what I am showing, let me show you one server, particularly so AMD Threadripper, so spec. If you guys put specifications, then we will get how many number of core is 64. Are you able to see my screen? AMD Threadripper is server processor, and which actually number of core is equal to 64 and number of thread is equal to 128. In one processor, we have 64 core. Okay, and each core having 2 threads, processor having 128 thread. Okay, so one processor having 128 thread, and a server may have multiple processor. Okay, and a chassis have a multiple server. Okay, so then rack. So these are way organized. Physically, you organize the thing. Okay, so whenever you have many such bigger system, then we need to connect. So either using bus is anyhow share media, lower cost, lower throughput, low scalability is poor. Then we need to go for switch network. So switch path, it is higher cost, higher throughput, scalability is better. So higher cost means this is not common bus or common media. So you require individual path. So these are the some questions. Interconnection, what is the topology, whether direct or indirect, where is the switching done, and then when is switching done. So then circuit switching or packet switching, how the connections are established. So in general in our parameters, so we connect using so LAN cable. Okay, LAN cables and putting into a big, what I can say, router, network switch, and how they are interconnecting. So we don't go detail about this store forward or centralized or distributed switching or synchronous or asynchronous switching. We don't go detail about this. But ultimately, so there are two kind of connections. So one is direct connections and other is actually indirect connections. It connect through the switches. So in the left side one, this is one processor, one machine. One machine have actually what I can say, PMS. P means processor, memory and switch. Processor, memory and switch. And each left side one, they're connecting 4 machines are there, and each machine are connecting to the other machines directly. Okay, so this machine get connected to this machine through link. This machine and this machine is connecting through this link. So there are how many links? So 1, 2, 3, 4, 4 links, and they're individually connected. Okay, and directly connected. This machine is get connected to this machine directly, and this one is indirect connections. So these machines are connected to switch, and through switch, so this machine want to send data to this machine, you need to send to switch, you need to go through switch and come back. This indirect connections. And there are another kind, static network or dynamic network. Okay, fixed point-to-point network, usually in general direct connections, and each node pair may not have direct connections. Routing through nodes, it happens. In general, static node, whatever we read on our computer network courses, they use actually static networks. And what is dynamic network? The dynamic network connection established as per the need and usually indirect, and path can be established between any pair of nodes dynamically. So it is not packet switching or circuit switching. So what I am telling to say is actually connection get established on demand and based on the requirement. Okay. And this is static topology. This is static topology. So this is 358. So another 1 minute I'll take, not more than that. So this is a static network, and this is 4 machines connected using linear connections. So in this 4 machines connected in linear, how many link you require? So 3 link. This is 1 link, this is another link, this is another link. 3 link you require. So this is star network. 5 machines connected using star network. One is master or central one, and you require 5 link. This is tree network. This is mesh network. Different network have different properties, different what I can say characteristics. So how many links you require, how much bandwidth it can suffice, how much what I can say bisections bandwidth you have. That many parameter, using many parameter you can compare the networks. Okay, different kind of static networks. This is another kind of static networks. So ring networks. Okay. Ring network. So in this case, even if one link is failed, still at least you will get another what I can say connecting path. This is fully connected one. This is torus one. This is torus and mesh. Mesh have actually wrap around. If all the cases it is wrap around, then it will be torus. So this is mesh. If you do a wrap around all the cases, then it will be torus. Okay, so next class. So tomorrow there will not be classes. Okay, so I am going out of town. So tomorrow there will not be classes. The makeup class will be announced later on. Hello, student. So tomorrow there will not be any classes. Makeup classes or this tomorrow classes will be announced later on.
Okay, sir.
Okay, sir.
Sir, like even in a dynamic, when we say dynamic connections, so even in that case, there are some the connections are fixed. We have different routing, and
So
that would even happen in
told
stack.
you dynamic connections. I am not saying routing. So because packet switching and circuit switching, both are different things. We cannot say they are static network, dynamic network. Dynamic network. So will come. I'll show you some example. What is dynamic network? Okay.
Okay. Okay.
So network get interconnected dynamically. Okay. So connection get how it establishes, that is different issue.
Okay.
So have you heard about this London Bridge is falling, that songs? So the path get interconnected by creating means road get created and road get open. You can disconnect the thing and connect the thing. And the things, the link get connected and disconnected whenever you require. Okay. So I'll give you proper example, base network and base network, bench network. So what is dynamic network also I'll give you some example. Okay.
Okay, sir.
So from this class onwards, now everything will treat mathematically. So no program business. Till our quiz one, all programming business was there. So till quiz one, all the programming business were there. Now everything will analyze mathematically. Everything will be pen and paper based.
Excuse
Okay,
me, sir.
thank you. Yeah.
Sir, I had a small doubt. Can I ask?
Yeah, sure.
So, in like before the quiz one, there was a slide that mentioned that loops are bad, right? For loops are bad because there is branching in for loops, right?
Mhm.
There are jump statements. So why are jump statements bad? Like the first reason, is it because of pipelining, because the pipeline has to get emptied before every branch statement, or is it because of cache misses which happened due to this branching? Which one
So
of that?
what I am saying, branching means not the loop branches, loop based branches, but other EPL statement and other statement if you are putting inside the for loop, then it is bad.
Okay, that is different. No, the example was like this. There were two for loops and for loop one, for loop two, and we had benefit with by when we merged both the for loops. I actually ran this code and there was a significant overhead. Well, there was like the like two for loops ran in 3 seconds and like single for loop ran in something like 1.5 seconds. Like this is very confusing. Why is there such a difference in merging for loops? What is the overhead here?
No, internally what I can say, you can take benefit of cache. Also, you can take actually not only that, it can actually pipeline very nicely. EBF reduces the branches.
Okay, so it is pipelining. So which one is it main? Pipelining is the main thing, or is it the cache misses? Like which one is it?
Both the things.
Okay, both of them. Okay, fine, sir. Thank you.
And on top of that, you can symmetrize also. You can vectorize the code also. If you compile with -03, if you have in between, you have suppose what I can say if else statement, it will not do the vectorizations.
Okay.
So it can vectorize out. So three things: cache also you can take benefit. You can take subtly pipeline also you can do. Also you can symmetrize the things. You mean vectorize the things.
Okay, sir. Thank you.
Okay. Okay. Thank you.